This presentation is the first in a series we're going to do on mathematical or symbolic logic, which is the way mathematicians take formal logic and apply it to analyzing mathematical concepts. And to do that, we're going to start with this basic logical unit, what's called a statement. And there's a mathematical definition of a statement. It's a declarative phrase or sentence that is either true or false. And the emphasis here is that it's unambiguously true or false. It can go one way or it can go the other. There's no third option. There's no room for confusion or interpretation. And I've got two examples of statements here. It is raining and I am wet. These are both either true or false. Either water is falling from the sky or it's not. Either there's water on you or there isn't. And it's unambiguous which state you're in. Now, you could be sitting there thinking, well, is it raining? I look outside and, is it drizzling? Is it really raining all the way? And, the same thing with I am wet. How much water has to be on you? With English statements, there's always, almost always, going to be some degree to which you could argue the point. When we're talking about whether or not an English statement is a logical statement, we kind of want to avoid being excessively picky like that. If there's water on you, there's wet, and we don't want to get involved in a big debate over how much water is required and so forth. If there's water on you, you're wet, the statement is true or false. Now, on the right-hand side here, I have two examples of English statements that are not logical statements. And for both of them, it's because there's just too much possible ambiguity. With the first one, for example, the television is large. It's this word large that causes trouble. What constitutes large? A television that I think is large, you might not. A television that, for example, a 6-year-old thinks is large, an adult might not. There's just too much room for interpretation there over what large means. Similarly down here with the cat is brown. Where's the line between brown and tan and brown and orange? And there's just too much ambiguity there for us to classify that as a logical statement that is unambiguously one way or the other. So now that we have this definition of a simple statement, if you will, let's look at how we can combine these together into more complex statements, what mathematical logicians call compound statements. You've got a simple example of that here. I took the two statements from the previous page, it is raining and I am wet, and I combined them together using this logical operator, using the English word and. Now you might notice here that I left some things out. I left out capitalization, I left out punctuation. So this is really not a grammatically correct English statement, and I did that on purpose. You'll find as we get into this that sometimes the rules for interpreting logical statements, the logical rules, don't always match up 100% with the English rules for evaluating English statements. So that's why I've kind of left these as grammatically incorrect. Is I like for you to kind of get clear right up front that you need to be thinking of these as logical statements, not English statements, and kind of leaving out the grammar, to me, kind of helps distance us from the English rules that sometimes aren't going to work so well here. Okay, now, being mathematicians, we don't want to really deal with specific statements like this. We want to have a way that we can generalize these statements so that we can kind of deal with them as a class instead of trying to handle every possible statement individually. And if you've taken even just a basic Algebra 1 class, you're not going to be at all surprised with the way I do that. We're going to use variables. And that's what I've done here. I've taken the first statement, it is raining, and replaced that with the variable P. And I've taken the second statement, I am wet, and replaced that with the variable Q. So now I've taken the first step in taking this English statement and converting it into a logical or a symbolic statement. And, mathematicians love their symbols, so I'm actually going to take this a step further. I'm going to replace the and with this kind of an upside-down V, and this is going to give me what's referred to as a logical and, this statement here. And if you saw this in a textbook, if you were to try to read this, you would read it exactly the way it is here on the second line. You would read this as P and Q. Okay, so the next statement that we're going to add to our toolbox here is kind of the natural English statement. I'm going to replace that and. I've got the same two logical statements. It's raining and I am wet. And this time I'm connecting them with the English word or. And I'm going to translate that into a symbolic statement the exact same way. It is raining becomes P. I am wet becomes Q. And I have a new symbol here. The symbol for or is this kind of stylized V. Looks a lot like a V, but the font is a little different. So it's kind of a V shape. All right, so there's one more statement that I want to add to our little toolbox here, and that's a logical not. We're going to represent that with this little wavy line. It's called a tilde. It's actually the English word for it. And it's equivalent to the word not in English. It just reverses the meaning of the sentence. So it changes it is raining into it is not raining. So now we've got three tools in our toolbox, and I've summarized them here on this slide. We have the English name in the first column, and, or, and not. There's actually a mathematical name for all of these. And is called a conjunction, or is a disjunction, and not is a negation. And I've listed the symbols. These are the ones we saw on the previous slide here. And in the last column, I have an example of each of them. Again, it's the same things that we saw on the previous slides. Now, for those of you who have maybe studied a little set theory, these and or symbols may look a little familiar, and that's actually not a coincidence. The logical and is equivalent to set theory's intersection, and the logical or is equivalent to set theory's union. So I'm not going to get into set theory here, but if you're familiar with it, you can kind of keep that in the back of your mind as kind of the set theory equivalence. So this is where we're going to end this presentation. In the next one, we're going to start to look at ways that you can evaluate these compound statements, and way that we can compare two compound statements to see if they are actually logically equivalent to each other.